Another paper from James Chen then. This is a paper 2 TMUA paper. It was really good fun to take. There are a lot of pop culture references in this paper. Rick Astley claims that he is never going to give you up. Which of the following is necessary to disprove his claim? He will always give you up is not necessary, right? Because he doesn't have to give you up every single time. He's claiming that he'll never give you up. So therefore, if he does that even one time for one moment, then therefore he's breaking his promise. And so two only is the one we'll go for. This is a song, and I only know that because it played at a cricket match that I went to the other week. So vertical lines of symmetry. Well, there's one on H, there's one on O, there's one on all these except for G. So there's six there, and then for the lowercase, it's only on the O's, and then 3 minus 6 1 is 3, right? So yeah, cool. Next question, Taylor. So Taylor claims to the boy next door, "You belong with me." A cheerleader, a popular cheerleader, hears the claim and responds, "There exists a moment in which the boy does not belong with you, Taylor." That's a negation of Taylor's claim, right? She's just saying that Taylor is claiming that this person always belongs with her, and well, sort of, and this person is saying it's kind of like question one, right? Like this is they're doing the least work possible. They're saying that if there's even a moment in time in which that boy does not belong to you, Taylor, then your claim is wrong. So it's a negation, and it's very intelligent from the popular cheerleader to be able to form a negation of a statement properly, and I'm very impressed with that. So yeah. Anyway, powers of two go like this, and then we just need to find a pair that make 160, which is these two, and there's clearly nothing else that does it because like you can, this is too small, like it's less than half of 160, so yeah, so just two of them because of course you can swap them over, right? So one pair is 32, 128, and the other is 128, 32. So yeah, um, I'm not sure whether this is a reference that I'm supposed to get. Probably not. I don't know. I mean, probably because I'm not going to get very much. But the probability that two of them share a birthday is P. The probability that James shares a birthday with someone else is Q. Now, the probability that James shares a birthday with someone else is necessarily smaller than the probability that at least two of them share a birthday because James is just a or James's relations to everyone else is just a subset of everyone's relations to each other. So P must be bigger than Q. Um, and then the probability that no two share a birthday is R. Now, a fun fact is that it takes 23 people in a room to have a greater than half chance of sharing a birthday anywhere in the room. So therefore, if there's only five of them, then this probability is less than a half, or P is less than a half, and therefore R is bigger than a half. So it looks like this, and we find this one down here for our answer. So yeah, the first time is 67, which means the second time is this, and then the third time is just this times this again, which is that. And then this just makes a geometric series. You're timesing by sine to the 67, cos to the 69 every time. And for that, for the sum to converge to infinity, you just need the ratio, mod ratio, to be less than 1. The thing is here, though, that cos and sine are always bounded between minus 1 and 1. And they're never equal to 1 together at the same time, and they're never equal to minus 1 together at the same time. And one of them's never 1 whilst the other one is minus 1, because they're only off by like 90 degrees. So, so this is just always true, right? It's just always true. The only case in which it wouldn't is if it was like 1 times minus 1, but that's just not the case. So this is just always true, and it's just always for all real values of x we can go with. How many solutions means this is a drawing question, so there's a couple of ways you could do this, but I just divided by e to the x and said that this graph is e to the minus x, which is just a translation of e to the x in the y-axis because of the minus x, f of minus x. So it just looks like this, right? It's just the e to the x graph going the wrong way. And sine of x is, of course, just sine of x between 0 and 2 pi. I've put e to the x all the way up here because, of course, e to the 0 is 1, which is the maximum that sine takes anyway. And then, of course, if you're just going between 0 and 2 pi, there's only two solutions there. So we'll just go with 2, and we'll be done. And that'll be it. This is a proof of this claim here. Unfortunately, it's wrong on the first line because x minus y all squared is not bigger than 0 always. It's bigger or equal to 0 because, of course, x could equal y, which it hasn't discounted up here. So, yeah, it's incorrect on line 1. So, yeah, we'll underline that one because, yeah. Number 9, this is almost certainly a reference that I don't understand and couldn't be bothered to look up. All that really matters here is that the sequence just goes she got away, and then she got away, and then she got away. It just goes over and over again. So all that matters is what this number is, modulo 3, or as in if I were to find what that number was and divide by 3, what's its remainder? Because if its remainder is 0, then the word is she, and if its remainder is 1, then it's got, and if it's remainder 2, then it's away, and if it's remainder 3, same as remainder 0, it's she again. So let's just add all this up. Now, there's a bunch of ways you could do this. I said there were 76 terms here, and a fun fact about 3 consecutive numbers is that they're always divisible by 3, because it doesn't matter which one is the multiple of 3, the other two, one above and one below, so they all cancel out. So there are 75 kind of triples here. No, there aren't, sorry. There are 25 sort of triples here, all of which add up individually to a multiple of 3. So the first 75 terms get you to 2099, and adding all that up is definitely a multiple of 3. So all that matters is the 2100, but of course that's got a digit sum of 3. So that is also a multiple of 3, which means the whole thing is a multiple of 3. So the remainder is 0 when divided by 3, and so therefore it's one of the she words. And yeah, we're done. A student believes this because they're, really, really dumb. And they want to evaluate p squared, where p is this. So p is squared is a plus b all squared, which is this, of course. Now, their answer is a squared plus b squared. So the difference between the correct answer and their answer q is just 2ab. Now, the quadratic that has roots a and b is just x minus a into x minus b. So if we expand this out a little bit, we get this. I could have written minus ax minus bx, but I grouped them up because I kind of knew where this was going. P is a plus b, so I can group them up and replace that with p, and q is ab over 2, so replace that and then just times everything by 2, I guess. And this quadratic will have roots with a and b, I think. Okay, so when writing a TMUA question, you write end statements, blah, 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 blah. Basically, what this is saying is, if we look back at question 1, as it kind of tells us to, if you've got a bunch of statements like this and you want to write all of the multiple choices such that any combination of any of the statements is kind of included in the set, then how many statements do you need? So for example, here, there's one that says neither of them, then there's 2 used up to say one each, and then there's 1 to say both of them. And if there are 3 statements, you'd say neither of, or none of them, then you'd have 3 things saying 1, 2, and 3. Then you'd have 3 things going 1 and 2, 2 and 3, 1 and 3. And then you'd have a last statement that says all 3 of them. So that's kind of what this is saying. But this is just adding up choose functions, right? So if you've got n statements, you'd have one statement, which is n choose 0, which is to say none of them are true. Then you'd have n statements, each of which were saying, 1 only, 2 only, 3 only, and so on. Then n choose 2 is how many ways you can take 2 of the statements and claim those are true, and blah, 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 up to the last one that says all n of them are true. And so it's just this, which is shorthand for this, of course. Well, this is shorthand for that, I guess. Some of you may know that if you do this with any number n, you end up with 2 to the n, which I think is where these answers are coming from, but they're not quite right. So it is just this one here. These ones are just off by a little bit. So kind of interesting. Those are some of the options, but yeah. Which of these numbers is the smallest? So this is 67 factorial over 69 factorial. I'm not sure why 67 and 69 are being used so much. They were used earlier in a question as well. Anyway, this all cancels to make 1 over 68 times 69, which is certainly quite small. This is the same thing, but upside down. Of course, if it's upside down, that means the 69 is on top. And then you end up with the 68 and the 69 on top, which is obviously quite a big number, so that's going to be gone. This is the 7th root of 6, which is a little bit bigger than 1, because if you're less than 1 and you start powering up, you end up going even lower. These sort of tend to 0. So this must be bigger than 1, and this is not bigger than 1, so this can go away too. This is 1 over that same thing. But I'm going to say that this is quite close to 1. So 1 over something quite close to 1 is a bit less than 1, but I don't think it's very much, particularly when compared to something like this. And this is 1 over 68.5 times 68.5. Now, I obviously couldn't be bothered to calculate these things. There's probably some algebra I could do to check which one's bigger, but in the end, I just decided the fastest way to check is to do something like this and say that's 1/12. And this is 1 over 12.25. I just happen to know what these things times to make off the top of my head. So therefore, this one is the bigger one because you're dividing by something smaller. So this is the smallest one, so I decided to just extrapolate that same logic and say that this one is therefore the smallest one as well. And that's probably true. Anyway, so here's some conditions about 5 TMUA scores. The range is 10. Let's start with, no mode, the median is not a mode, there are 2 modes. That means these 2 and these 2 must be the same, and this one's different and between them, because that's the median. The mean is 32, 32 times 5 is 160. So if I call these 2 A, then because the range is 10, these 2 must both be A plus 10. And then if I take away that all from the total, I get 140 minus 4A. Now, because the median is not one of the modes, A must strictly be less than this, which I can then solve to get that. And over here, A plus 10 must be strictly greater than that, which you can solve to get this. And because A is an integer, because everyone's score is an integer, and it's bounded between 26 and 28, I think that means A is 27, which is the lowest of the scores. These are all the scores, just in case you're interested, which you're probably not. Question 14 then, so f is continuous, blah, blah, blah. It's got what condition is exactly one root in this interval here. Now, exactly one root rings alarm bells because exactly one root is quite a hard thing to guarantee, I think. So let's watch all these rules fail then. So if f of minus 1 is negative and f of 2 is positive, that doesn't say anything about whether there's a root in here, because the root could be at like 1.5, like it could just gradually go from minus 67 up towards 0 at about 1.5, then cross the line and then go up to 67 at 2. So that doesn't, this is, no. This one fails for the exact same reason, just backwards. And this one looks good because you start at minus 1 and you down at minus 67, and then at 1 you're at plus 67. But you could go down from minus 67, up, down, and up again and have 3 roots in that space. So no, none of them. Exactly one root is a little bit more tricky to say than just those things. Anyway, the nth root of 2 is irrational. The proof begins as follows. Good. Then we just raise everything to power n. Just cool. This is nice. Which of the following is most useful? So I've seen this before, which does help, and it's really, really lovely. You just times everything by s to the power n, and then you break this up into s to the power n plus s to the power n. And by Fermat's last theorem for n bigger than 2, this has no integer solutions, which is what you want, of course, if R and S are integers here. So therefore, this Fermat's last theorem is going to be quite useful here, which is just a lovely way of proving it. So yeah, cool. Which of these is a negation? So it starts with for all, so we should have a layer exists, which they all do. I then skipped to the end and said, well, you want to say not this thing at the end here. Not this thing is greater than or equal to. Greater than is saying too much, right? Because you could be equal to as well. So we'll get rid of the ones that have greater than in them because we want to be greater than or equal to. That's the equivalent of not less than. Not less than is greater than or equal to. And then we need to say, well, this is claiming that for some conditions here, if this is true, then this is true. So the negation will be there exists a case somewhere in here where this is not true. And I think this is the one that says that. There exists a case somewhere in here where this is not true. So I think it's going to be this one down here for our answer. Cool. Question 17 then, playing Wordle. So the good news here is that we know what the numbers are. They're 3, 4, 7, 8, and 9. So we've got 5 numbers here. We know these are the ones. We know 7 goes here in every single case. Now it gets a little bit annoying to figure out the other cases here because there's quite a lot of kind of like overlapping conditions. So what I decided to do was say, firstly, let's just put the 9 here. So I'm not putting the 1 here. I'm just saying there's one choice for this number because I'm going to times all the choices together, of course. I'm just saying the 7 goes here. Let's just put the 9 here. Of course, only the 9 and the 3 can go here because the 4 and the 8 can't. So let's put the 9 there first. And then once the 9's here, the 3, the 4, and the 8 can go in any of the other positions, right? So let's just put any choice of 3 there. Then the 2 that remain can go there, and then the 1 that remains can go there. And we'll times them together to get 6 options. But then what happens if instead, obviously we still put the 7 here, what happens if instead we put the 3 here, right? And now we know that the 9 can't go here either. So what I'll do is I'll just place the 9 here, and then say the 4 and the 8 can go in some choice here, and then whatever left goes at the end. And then the last case would be, what if you put the 7 here and the 3 here, but then put the 9 here instead? Then you can say the 4 and the 8 can go here, or they can go over there. 2 choices, and then the last one goes there, and then add up the cases together, and we'll have 10 in total. Just, there's probably smarter ways of doing that, but I thought that was quite a safe way of doing it. So yeah, we can expand this out here to make this, I guess. I sort of know things about roots of polynomials, which makes the expansion quick. But it doesn't really matter. All I'm saying here is looking at the x squareds. So x squared comes from x times minus c, or x times minus b times x, or minus a times x times x. So that's just this, and that equals minus a. And likewise for the x's, you do x times minus b times minus c, or minus a times x times minus c, and so on. There's 3 of them, and you get this, and that must be equivalent to b. And then the last number should, of course, just be this times this times this, which gets you minus c. Cool. Now, there's a bunch of things we can do here, including cancelling the minus a's and timesing by minus 1, I guess. This means b is equal to minus c, which I think I just put into this equation. Also here, the c's cancel because everything's non-zero, and also times everything by -1 to get this. Now, if I replace the c's here with minus b, I think is what I did, yeah, then these two things cancel, and you end up with, oh, I also divided everything by b because again, it's non-zero, and you end up with b is -1, which is, yeah, you just get there straight away. Cool. Yeah, I forgot how that ended, but sure. So you have a triangle, side length 1, 5 points plotted in around the triangle. So what this question is kind of asking us to do is to space our points out as much as possible, um, and find the d such that our points are always within sort of, at least, no matter how hard we try, at least a couple of the points are always d apart. So like it's easy to go, well, okay, you can just put a point here and 4 of them up here, but then 2 of those 4 are 0 apart, right? So we're trying to space everything apart to have a distance that's as big as possible between any two pairs, right? And what's the distance we can find that we're guaranteed to be within? So it seems sensible to put 3 of them apart like this, and then just try and shove the other 2 in the middle somewhere. Now, if you put another one down here, of course, now you're half away. You could go into here somewhere, um, like in the middle, but then you end up being very close to basically anywhere else you could try and put it. So if you put it down here, you end up trying to make, or making like this well-known 4 equilateral triangles inside of a triangle idea. And your fourth point, or sorry, your fifth point could easily go on the corner, on the another corner of one of these triangles. And of course, each of these triangles has length 0.5. So that makes a 0.5 construction. And I don't think that there's, I mean, this is TMUA, right? So you're not going to sit here and prove. I'm sure you can probably Google a proof of this. But it made a lot of sense to me that once I'd drawn this, that there's no way to do better than a half. Because the moment you nudge any one of these, you bring it closer to another one of the points somewhere in the picture. So yeah, I think a half is probably, if you just put the other x somewhere here or here, I think a half is probably the answer. Question 20, this 5 squared is obviously very sus, and I was kind of assuming that someone who sent me an email, this is just my ego talking, but anyone who sends me an email with stuff in it that they want me to do, I assume they've watched a fair few of my videos. So as soon as I saw this 5 squared and this 5, I was like, oh, actually, you could just use the quadratic formula here, but use it in terms of 5. I made a video on this one day, a long time ago, where you just pretend the a term is 1 because it's 1 times 5 squared, and the b term is, I guess, minus 2x squared plus 1, and the c term is all this, and you just make the quadratic formula with 5 equals. And I didn't actually think this would work, but it did work, which is great. When you expand this out, you just get this, and then the 4x4s obviously cancel, which gives you something squared on the inside of this bracket, 2x plus 1 all squared, which is great because, I mean, technically this and the square don't really cancel very well. They cancel to make mods 2x plus 1. But I think because we're plus minusing it anyway, that doesn't really matter, because if the thing was negative, you'd times it by -1 and take it away. But because you're planning to either plus or take away it anyway, I think that's fine. So yeah, we'll just cancel this out and make this. And then, of course, go with either the plus solution or the minus solution to get either this, which turns out to be this, which ends up being this. I just sort of very quickly completed the square. Or you use the minus solution, which gets you this, down to this, which gets you this. And now we look at the answers they've provided. And if we factorize out a half from this one, we end up with a -1. So I think q needs to be 2 and p is 17. And then over here, if we factorize out half, we get 1, which must be r. And then s is 21, I guess. And then when we add all those together, we'll end up with 41. Thank you for writing that paper, James. Again, that was great, and really enjoyed it. I hope everyone else did too.